Okay, we are on. Actually, before we start doing anything else, example 1 yesterday, we looked at the graph. We looked at the function, just good old-fashioned parabola, y equals x squared. And we found out that its derivative, which means the equation that represents its slope everywhere, is y equals 2x. Now, you can kind of see from the graph that it makes sense that it's that, because look at the way the line y equals 2x behaves. It goes through 0, 0, which makes sense, because at the point where y and x are 0, you'd have a tangent line that would be horizontal, and horizontal lines have a slope of 0. So it makes sense its slope is 0 at 0. And then, of course, you can realize that everything to the left of 0 has a negative slope. Everything to the right of 0 has a positive slope. And that makes sense when you look at the line. Right? And if you're ever not sure if you have the right line, you do realize, I pointed out yesterday, that Desmos actually does know how to do derivatives. If you say y is the derivative of x, some people in my notes thought that I was writing f to the power of 1. I actually got the message on SB saying, why is that a power of 1? It's not a power of 1. Sorry, that's my bad writing. That is an apostrophe that we would say prime. So f primed of x is our notation for the derivative of x. There are other ways to write derivatives notationally, and we're going to get into that next class, not so much today. Today we're going to focus on graphing. So Desmos can graph, and as you can see, it's the same, right? Purple, black, it's the same line. We have it. But it would be kind of nice to show you that this line, of course, represents the change of the tangent as you go around the curve. You can actually make a line that shows what the tangent of this thing is everywhere, and we can do it with a slider. So now that we know that we have a derivative here, we have f primed of x, what we can do is we can say, all right, well, I would like a straight line. And okay, so we'll pause for O Canada, and then I'll draw the straight line here. Click that. There we go, we're live again. Okay, so like I was saying, I know that the derivative of this function is 2 times x. And our actual, our example 1 from yesterday, we actually wanted to find the tangent, or the slope at x is 3. So I wanted to know the slope at 3. So in this case, if x is 3, then the slope is 6, because 2 times 3 is 6. So I could actually show you that as a point, right? If I wanted to, I could just go 3 for x, comma, and then I know that 3 squared is 9, but you know, if this was a more complicated function, I could even let Desmos do the calculating for me. I could just go 3 comma f of 3, and it'll actually know that that's 9 and put the point down. And then, you know what I can do is I can show you the tangent at that point, right? I can very easily use the point slope form of the formula for a straight line and go y minus f of 3, right? Because so this is the y coordinate, so y minus the y coordinate equals the slope. And I already know that the slope is 6 at this point. But why don't I just use my derivative, f primed of 3, which is 6. So that's the slope, and then, of course, x minus 3. And there we go. We now have a tangent line at, here, let me kind of zoom back to the starting. Oh. There we go. That's a little easier to see. So there's the tangent line at x is 3. What if we wanted just a more general form of this? What if instead of point 3, we just said we wanted point A? And I'm going to say, yes, I'd like a slider for A. And then I'm going to make that f of A. And then instead of f of 3, I'm going to make that f of A, f primed of A, and A minus 3. And let's see. Oh, that didn't work. Hold on. Why didn't that work? F primed of A, and oh, oops. That's not what I wanted. I wanted x minus a, not a minus 3. There we go. X minus a. There we go. Now, as you can see, as I move the point along, you can see this the tangents change. And now you can really see that, again, starting at 0, let's see if I can get right on 0. At 0, of course, we have a horizontal tangent, right? Because the tangent line to any peak or valley, we'll call them local and maximums and minimums. In this case, it's the vertex. The slope of the tangent to a vertex, of course, has to be 0 because it's a horizontal line. And as I go to the negative side of the graph, the slopes are all negative, but they're getting steeper as I go up, right? And then, of course, as I go to the positive side of the graph, they're getting steeper as I go up that way as well. So there we go. All right, let's do another example. So today's notes, we're going to look at graphs some more, but at first we're going to do another example of just using our algebra to find the slope equation for 4 minus x squared. Okay, so it's called, again, using first principles. So let's see, what does this look like? Well, first of all, let's start with the formula. F of x, oh, hang on, I'm on the wrong page. There we go. There we go. F of x, or sorry, f primed of x, the derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so in this case, f of x is 4 minus x squared. So this is going to equal the limit as h approaches 0. And instead of 4 minus x squared, I'm going to replace x with x plus h. So that'll be 4 minus x plus h squared. Minus f of x. Now I'm minusing all of f of x, so it's actually very useful to put that in a bracket so that you don't goof up the negatives. And there we go. There's our derivative. And like has happened 100 times in this course already, I've got a situation where I can't plug in the 0 for h because I'd end up dividing by 0. So I'm going to do some algebra to see if I can make that not happen. All right, so let's see. This is going to be the limit as h approaches 0 of 4 minus, and then, okay, so I'm minusing all of x plus h squared. So x plus h all squared is x squared plus 2xh, but I'm minusing that. And plus h squared, but I'm minusing that. Then I'm minusing 4 and adding x squared because I distribute that negative through the bracket. And nice things happen here. 4 and negative 4 cancel. Negative x squared and plus x squared cancel. And I am left with, I'm just going to move up to here, I am left with a numerator that has every term with a factor of h. And that makes life good because now I can factor h out of the numerator. And divide it through the denominator. And I now have the limit as h approaches 0 of negative 2x minus h. I don't know why I wrote it like that. That looks really dumb. I'm going to stop that. Limit as h approaches 0 like that. That's better. Okay, so from there, I can actually now plug in my 0. So I know that f primed of x is actually going to be just negative 2x. All right, let's graph those two things. So f of x is 4 minus x squared. What does 4 minus x squared look like? Well, let's see. 4 minus x squared is going to have a y-intercept at 4. It has x-intercepts at plus or minus 2. And that's good enough. That'll give us a good sense of what the graph looks like. So this is f of x. And I'll use a different color here. F primed of x is minus 2x. So that goes through 0, 0. And it has a slope of negative 2. So down 2 and over 1, down 2 and over 1. So it's going to be something like that. Up 2 and over 1, up 2 and over 1, something like that. Now, what relationship do those two graphs have? Well, remember that again, right here, the tangent at a vertex has to have a slope of 0, which is why that point there, the slope is 0. Remember, that purple line represents the slope everywhere along the black line as x changes. Everything to the left of that 0 is a positive slope, right? All the slopes going up this way are all positive, which is why this purple line is above the x-axis. And then as I go this way, all of the slopes are negative. The further you go along, the steeper the slope is, which is why this is going up and down. And for the second time, we've now, or actually the third time, we've now seen that the derivative of a quadratic is linear. All right, let's just take a look at that on Desmos and see if that's what it looks like. So there we go. Okay, I'm just going to change around what I've got here. I'm just going to make that a 4 minus. There we go. And then we'll just move a around to what I actually needed to do. So there's the graph that we just did, right? And here's the changing slope as we go around. Notice it's always linear. Very cool. Okay. So let me just hide that, and okay, so this is our graph right here. Okay, and if you're ever not sure, oh, are we sure that we got the right graph? We'll see this. We had negative 2x. Is that the same? Is that the same graph? Let's see. Yep, black, purple, black, purple. It's the right graph. All right. Let's get away from algebra and just look at some graphs. Turn your page, and now you've got this thing. I don't know why I can't make this go away. There we go. Okay. Everybody can still see me, right? Oh, geez. What's going on over here? Okay, there we go. All right, so graphing the derivative. We can estimate the slopes of the tangents at various points on the curve. These give values for f prime of x. In particular, we look for places on f of x where the slopes of the tangent is 0, and these will be the x-intercepts on the graph of y equals f prime of x. So if this blue line here is f of x, I would like some sort of sketch that represents f prime of x. So let's see if we can kind of make one here. All right, it looks to me like I have a peak here at, it looks like this is 2.5, right? Right, we're counting by halves here. So negative 2.5, I should say. So I think we have ourselves a tangent line there that would be horizontal, right? And then at, okay, so actually I'm going to graph it below. So below, let me go back to black here. There we go. So below at negative 2.5, my graph should have an x-intercept. Okay, where else would we have an x-intercept? Let me go back to green. Looks like at about here. So what's that? That's just almost 1 to the left of 2. So almost 1 to the left of 2. So I think I have an x-intercept there. And I have myself an x-intercept up here. Right? Here's another spot where the slope is 0. Looks like it's about 1/3 of the way past the 4. So about 1/3 of the way past the 4. Something like that. All right, so there's my x-intercept. So now, how are the arms behaving between the x-intercepts? Well, tell me about all of the slopes from here to here. They're all positive, and they're all getting smaller, right? Think about it. A tangent here is very steep. Less steep, less steep, less steep, and then, of course, it works its way to 0. So it is a decreasing slope. It's always positive, but it's decreasing heading to 0. So I think that's an arm that maybe goes like this. Agreed? It's some sort of curve, obviously. Now, what happens after I get to this point? Well, now all of the slopes are negative, right? So they're negative all the way down to here when they start getting positive again. But what I want you to notice is that, see how steep some of these slopes are on the left? None of them feel that steep on the right. So I don't think that this thing's going to go down very far. I'm actually kind of not liking the way I drew this. I'm making it look like it's going to turn around at that point. It's not. It's going to keep, let me try that again. It's going to keep going. It's going to keep going this way, but I don't think it's going to go down very far. And again, why don't I think that? Because this is not very steep. In fact, I could probably kind of estimate that from here to here, that's approximately a slope of, I was going to say 1, right? That looks like a rise over run of almost 1. So somewhere around here, I should be at a y value of 1 on my next graph. Or actually, I should say negative 1. So where was that? Between there and there? Oh, I'm way too low. So I'm gonna fix that. I'm gonna go back and make that kind of just. Oh, see, that's still too far down. Oops. Oh, now I killed that line. Hang on. Where was that spot? Oh, hang on. I'll just undo. Ah, there we go. So I'm going to go. There we go. Something like that, maybe. And let's see, what's going on over here? Once I get to this point, all the slopes are going to be positive again. Again, from, say, here to here, that's a slope of about 1/2, so it doesn't go very high. And then after that, it becomes negative slopes, and they start getting steep again. So this doesn't go very high, and then it takes off that way. So I think it's going to look something like that. Let me put them both on one screen. There we go. I think it's going to look something like that. Now, there's a certain level of I'm just kind of guessing going on here. I kind of would like to know. I kind of want to know what this really is. And I have no idea what the equation for this line is, but I could probably come close. What do I know about this graph here? It's got some x-intercepts. So well, let's find what this graph is. Let's call this graph f of x. And let's find its intercepts. So it's got intercepts at -4, right? So that would mean it has a factor of +4. It has an intercept, I think that's 1/2. So that would be x minus 1/2. Looks like it has another x-intercept here at 3, x minus 3. And it has another x-intercept here at 5. So that's going to be close. That'll be where all the intercepts are. Oh, and you know what else I know? I know this thing has a y-intercept of 1/2. Can you see that? Well, right now, what kind of a y-intercept do I have? I have 4 times -1/2 is -2. -2 times -3 is +6. +6 times -5 is -30. So I have to do 2 things to all these factors. I have to times by a negative to get rid of the fact that right now my y-intercept's negative. And how do you turn the number 30 into 1/2? Well, you'd have to divide it by 60. So there we go. I think this function is something close to that. So I'm going to put that into Desmos and see if it's close to the same graph. And then I'm going to see if I have close to the derivative. Because again, I'm not a big fan of guesswork. I like accuracy in what I do. It's the physics training in me. Okay, so I'm going to just hide all these guys for now. I guess I could start a new page, but yeah. Okay, so. Oh, and I guess if I called that f of x, I'll have to call it something else. I'll call it g of x. G of x. Okay, so what did I say it was? I said it was -1/60th. And then I said it was, what was it? X plus 4. Thank you. Your memory's better than mine. And then I had, was it x minus 1/2? All the rest of the factors are negatives, right? Because they're all to the right of the x-axis, or of the y-axis. So x minus, what was the next one? -3? And then what did I say the last one was? X minus 5? That's pretty good. Compare, let's see, let's go back and, that's pretty close. I've got basically the right shape. I'll take it. And then, what is the derivative? Y equals g primed of x. And there, let's get the other one out of the way. And, oops. Oh, hang on, I shouldn't have done that. Undo, undo, undo. Oh, how do I undo that? Control Z. There we go. There we go. Okay, so I have the right basic shape. My scale is different. That's part of the problem. But it goes down at this x-intercept, doesn't go down very far, comes up, hits this x-intercept, doesn't go up very high, and comes back down to that x-intercept. I'm pretty happy with that, actually. I think my estimation here is pretty good, pretty close. So there we go. Now, what kind of a graph is that? Now, I could play with this thing and start to try to guess at its equation, too. But I see some people holding up 3 fingers. This is a cubic, isn't it? This, let's go back to the actual equation I was playing with. There we go. This is an x to the power of 4, and its derivative is an x to the power of 3. What did we notice on the last things we graphed? Things that were x squared became derivatives that were x to the power of 1. What do you think? What would be the overall rule for derivatives of polynomial functions here? Anybody want to try to put it into words? Don't all shout at once. What are you thinking? There you go. A derivative's degree is going to be 1 less than its original function. That is going to be true. All right, let's play with some more graphs. These are fun.
Mr. Keller, the pen trick works.
Yes, it did work.
Yeah, it's still working for you?
Yep.
Excellent.
We should spread the word on that. Let's let Miss Rashawn know in the library, because I'm sure she must have other teachers giving her this problem. So yeah, and what it is too is that there were other things in the forum. Where did I put the pen? Oh, thank you. There were other things in the forum. People were saying, oh, reload the software drivers and stuff. But it made sense that that was the problem here, because I remember I could even hear a little clicking when I shook the pen. The batteries were bouncing up and down because that wasn't tight enough. So yeah, I have not had a problem since I did that. Awesome. Okay, I'm glad that worked for you. All right, let's look at the next one, guys. Whoa! Okay, what would this thing be? Well, it changes direction 1, 2, 3, 4 times, so it could be an x to the power 5. So I'm expecting to get an x to the power 4. Okay, so let's see. Let's do this again, the logical way. I have slopes of 0 is what I was trying to say. Slopes of 0 here, 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 and here. Now, do these things line up perfectly? I guess they do. So I can just go down. And there's 1. Two. Oh, this one I kind of need some more room. 3. And 4. I think we got 4 x-intercepts. All right, what's this thing doing? All of the slopes leading from here to here are all positive, and the ones down here are really, really steep. So that's a very high, I think this thing shoots up like really, really fast this way. I might have even not made that steep enough. In fact, I don't like that. I'm going to make it steeper. Like curving steeper that way. Something like that. There we go. All right, and then it's not nearly as steep from here to here, but all of its slopes are negative, right? So from here to here, all slopes are negative, right? Because they're all going down. But they're not as steep, so it doesn't go down very far. So maybe something like that. what's happening between these two? Again, all of these slopes are positive, but none of them are very steep. It doesn't go, right? In fact, from here to here, that totally looks like a slope of rise 2, run 2. That looks like a slope of 1. So I think at my y-intercept, I think it's going to be 1. Do you get how I concluded that? The slope from here to here, I can almost kind of just estimate that as a straight line, as a rise of 2, run of 2. 2 divided by 2 is 1. So I think the slope at x is 0 is 1. And that's what I've drawn here. So I'm going to do something like this. Like that. All right, what's happening between the next two? Again, from here to here, this is a little steeper of a slope. This is a slope of 2 right here, right? Rise, or negative 2, rise of 2, run of 1. So I think at this point here, maybe, I have a slope of about 2, negative 2, I should say. So let's see, where is that point down here? Oops, I lost track of it. About negative 2. So something like this. And then it gets super steep again, right? Those slopes are going to be positively steep. So again, curve that up very sharply. There we go. I think it's going to be something like that. What kind of a graph do I have here? That's definitely an x to the power of 4. It's an even function. And we started with an x to the power of 5. So our hypothesis seems to be holding true, that the degree is always down 1. All right. Next page is some for you to try. So I have some sketches of them. I don't know how good they are, but I'll post those. I'll scan it and put it up so that you guys can see if you agree with mine. Now, there is a couple people in the room who've already done grade 12 math. Anybody know what this thing is a graph of? What is it? That is the graph of y equals sine of x. Those of you who haven't done the grade 12 course, you haven't seen trig functions graphed this way yet. But very interesting what happens to that one. So feel free to give these a try. I'll scan my pictures of them and post them. And of course, you could disagree with my drawings a little bit. I don't have the original equations that made these, so I can't just put them through Desmos. I could estimate them, I guess. And then, like I did on that last example. But there we go. That's graphing and trying to come up with the basic shape in a sketch form of the derivatives of functions. Okay, so let me stop my video.